some theorems that are useful when working with polynomials. First one's our remainder theorem, which simply says if you're going to divide by a linear factor, x minus a, then you know the remainder will be whatever it is when you substitute a into the polynomial. That'll turn out to be the remainder. It's easy enough to prove. Okay, remember, we can rewrite it as ax times qx plus the remainder. We're saying the divisor is x minus a. So I can rewrite the polynomial now as x minus a times the quotient plus the remainder. Now if I sub in a into the polynomial, well, in the first part, x minus a becomes a minus a. So that'll become 0. So polynomial a is in fact just remainder a. But remember, the degree of the divisor is less than the degree of the divisor. The degree of the divisor is what? 1. Therefore, the degree of the remainder must be, which means it's a constant value. So, remainder a is the same as remainder x, because it doesn't matter what I substitute in, it's going to be a constant value. So thus proving that remainder x is indeed a constant value. And so remainder x is remainder a, is polynomial a, thus proving our theorem. All right, let's use it. We're going to find the remainder divided by x minus 2. Well, all I've got to do now is simply substitute in. It turns out to be, as you can see, negative 19. That's certainly a lot quicker than having to do a polynomial division and then go, oh, right, there's my remainder. We can just bang, substrate in, get the answer. Now, a useful sideline to that is when it becomes the factor theorem. Because if it is an exact factor, what's the remainder? Very good. So therefore, we simply have to say, well, if x minus a is a factor, that means there's no remainder. So by the remainder theorem, polynomial a must equal 0. There is no remainder. So we're going to show x minus 2 is a factor of this particular cubic, and then hence factorise the rest of the polynomial. So polynomial 2 turns out to be 0, so yes indeed. By our factor theorem, it is a factor. Now, you could go and do a polynomial division now to go and find the rest. So if I did that, let's see, we get x squared, and keep going, 2x minus 15. Sure enough, the remainder turns out to be 0. But that's really a waste of time when you think about it. What was the point of having the factor theorem if I was only going to go and do a polynomial division anyway? Because I could have done that and gone, oh, look, my remainder is 0, so therefore it's a factor. So, all right, so there it is. Personally, what I would have done is I would have used the factor theorem. So I know x minus 2 is a factor, and then I'd just do it by, well, what they often call inspection, but it's logic. Because we know the leading term times the leading term must equal the leading term, and the constant times the constant must give me the constant. Because when we expand out, that's how we'd end up. So if the leading term times the leading term is the leading term, I know x times something is going to be x cubed. Well, it's got to start with x squared. So that's got to be x squared. And I can do the same thing with a constant. I know the constant times the constant must give me the constant, so negative 2 times something will give me 30. Negative
15.
Very good. Negative 15. Now all I've got to do is work out the missing term. So I can work out how many x's or how many x squareds do I have at the moment, and then work out the balance. So I'm using the x's. If I was to expand out now, how many x's would I have? Well, there's only one combination that's going to give me an x, and that's going to be the x times the minus 15. No other pairing will come up with something x. So if I was to leave it like this, I'd only get minus 15x. But I want minus 19x. How do I get from minus 15 to minus 19? 11? It wasn't a trick question. Minus 4. Minus 4. So logically, the missing term here, which will be something x, times the negative 2, must give me that minus 4x. So minus 4x equals minus 2 times what?
2.
Close. Oh, very good. Okay, so yeah. 2x. And there's our factorisation. And then we've got a quadratic. And quadratics are always easy. What multiplies together to give minus 15, adds together to give 2. Very good. 5 and minus 3. We were close. Let's try another one. Here's 4x cubed minus 16x squared minus 9x plus 36. Problem is this time they haven't given me a hint as to one of the factors. But that's all right, because we know that the constant must go into the constant. So I don't just randomly pick numbers and go, I wonder if 7 will work. No, it doesn't, by the way. I wonder if 3 will work.
Yep.
Oh, it does?
Could,
Oh, possible. Possible. Why is 3 possible?
Because 3 times 12.
Yeah, exactly. It's a factor of 36. So in fact, I could try any of the factors of 36, and it would be silly to try any other number because it's not going to go to 36. Oh, by the way, we could have negative numbers as well. So there's all those numbers with negative. So it might have a fraction in there because you might have a factor that says 4x minus 1, say, and then x would equal a quarter. And a quarter would be a possibility. So we also have to take into account the coefficient of x squared. So what happens is the answers must be in the form the factors of the constant divided by factors of the leading coefficient. That's why monics are so easy to factorise, because the bottom of the fraction becomes 1. You know you're dealing with whole numbers. It's possible here I'm not dealing with a whole number. So I could have 1 quarter, 2 quarters, 3 quarters, 4 quarters, 6 quarters, 9 quarters, and so on. I'll get rid of those ones because we've already got them. 4 on 4 is 1. So there's one I don't have to check. 12 on 4 is 3. Don't have to check that one. 36 on 4 is 9. So I don't have to check that one. But 2 also goes into 4. So maybe the factor is a half. Or 2 on 2, or 3 on 2, or 4 on 2, or 6 on 2, and so on and so on. But again, some of those are repeated. So we'll just cross out ones we've already tried. And it could be negative as well. So, what is going to be a logical one to try out of all those possibilities? What would be the one you would do first? Really? I'm pretty sure I'd go for 1 first. It's so easy to substitute in and hope 1's a factor. So, of course, I went for 4. You cheated. You looked at the sheet. Okay, let's see how we go. Oh, it works. That was lucky. So, okay. I now know x minus 4 is a factor. Let's do it by inspection. Leading term times the leading term must give the leading term. Therefore, over here I must have, don't cheat. Don't cheat. Constant times the constant must give the constant. So, now, let's see. You could do the x squared, you could do the x's. It doesn't really matter. You do the x cubes. No, we've done the x cubes. So let's have a look. What do we got? So, okay, you're going for the squared ones. At this stage, there's only one combination that will give squares, and that's minus 16x squared. We've got minus 16x squared, so we don't want to do anything. Of course, it would have worked if you checked the other one. If you did the x's, minus 9 times x gives you minus 9x. So again, it confirms there's nothing more to do. Except, of course, factorise 4x squared minus 9. So the other possibilities that would have worked out of all those possibilities would have been minus 3 on 2 and positive 3 on 2. Gosh, lucky we tried 4 first, hey? Let's have a look at this HSC question, 2004. They've already partly factorised it in a weird sort of way. They've gone, the polynomial is going to be x plus 1, x minus 3, quotient x, and then the remainder is ax plus 1 plus b. So they've sort of grouped it with an x plus 1 for some reason. I'm sure there's logic in there somewhere. Polynomial, here's probably why. Because when a polynomial is divided by x plus 1, the remainder is minus 11. When polynomial x is divided by x minus 3, the remainder is 1. What is the value of b? Well, they've given us some information. They've told us polynomial minus 1 is negative 11. Because when we divide by x plus 1, the remainder is negative 11. If we sub that in, and I guess that's why they've written it in this strange way, because the x plus 1 will become 0, that will become 0, and so we're just left with b. b is minus 11. Nice quick little question to start off with. So that's probably their gift mark for that question. What is the remainder when it's divided by x plus 1, x minus 3? Well, the other piece of information they've told me is that when we divide by x minus 3, the remainder is 1. So let's see what happens there. Polynomial 3 is equal to 1. When I substitute that in, I get that 4a plus b is 1. But in part I, we worked out b was minus 11. So we can work out a. a is 3. So now I can go back and work out the remainder. If I sub in 3 for a, and what was it? Minus 11 for b, we come up with 3x minus 8 as the remainder. So there's that, 3x minus 8. Okay, what are we doing this time? X cubed minus 2x squared plus 8. We're dividing by x plus 2. Get a remainder of 3. Find the value of a. Have we got enough information there to do that? What do we know? What is this question actually saying to me? Hasn't spelled it out as nicely as the last one. But what is it basically saying? We've got our polynomial. They're telling us something. Yeah, that's basically what they're saying, isn't it? When we divide by x plus 2, we get a remainder of 3. So sub in negative 2. Polynomial negative 2 is 3. Sub it in into the left-hand side. And we can work out a. And there it is. A becomes 19. All right. What about this one? Polynomial is divided by x plus 1, x minus 4. Quotient is qx. Remainder is rx. Y is the most general form of Rx given by Ax plus B. Ooh, questions where we have to give word answers. What do I think this is? English? Well, what do we say? Y is the most general form of Ax plus B. Yeah. The degree of the remainder has to be less than the degree of the divisor. Well, we're dividing by a quadratic, so the degree of the remainder would be a linear function. Might be a constant, but we don't know. Best we can say is linear function. You always go for the highest it could possibly be. So Ax plus B. So, all right, we mentioned about the degrees. That's what they're looking for, that you know the degree of the divisor and degree of the remainder relationship. Given that polynomial 4 is equal to minus 5, show that remainder 4 is equal to minus 5. Okay, let's just sub in. Polynomial 4, and there it is, minus 5. Okay. Because remember they've said given that polynomial 4 is minus 5, so if we just sub in, we get polynomial 4. On the right-hand side, we're left with remainder 4, so it must also be minus 5. Further, when the polynomial is divided by x plus 1, the remainder is positive 5. Go and find the remainder. Okay. Well, we now know remainder 4 is negative 5. That's what we just worked out. So 4a plus b is minus 5. Because remember, the remainder is ax plus b. Polynomial minus 1 is equal to 5. Because they told us now that when it's divided by x plus 1, the remainder is 5. Sub that in, I get minus a plus b is positive 5. Simultaneous equations. Two equations, two pronumerals. Should be possible to find both of those pronumerals. So we get A is -2, B is 3. That doesn't answer the question because they've said actually find the remainder. The remainder is AX plus B, so it's minus 2X plus 3. So they won't always be worded in the way you're expecting, I guess is what we're saying here. Okay. All right, little note there, because the factor is 2x minus 1, so remember the factor theorem for that would be use a half, because basically it's whatever solves the factor. That's what you substitute in.